trying to stream these to the outreach, but we have the recording to fall back onto. All right, so we'll go ahead and get started. I want to thank everybody for coming, and I want to introduce you guys to Kourbelas. He wears many, many hats on this campus and in this community, so we're really grateful to have you here. One of his biggest hats was having an office with my husband Chuck, so having to put up with Chuck was something else for him, huh?
Well, our office is now a storage closet.
Now it's a storage closet, yeah. All right, well thank you, Neil, for coming.
Well, thank you for showing up and inviting me. Like I said, this is my second time here, so they don't learn from their mistakes the first time. They invited me back. And I see a couple of my former bosses out there, so yeah, the pressure's on. But my probation officer isn't here, so that's good, you know. Okay, let me start out with this clip. Let's just see this. You've probably seen this before, but
people think that when they take math in school, there's the common response like, I will never need to use this for the rest of my life, as they learn trig identities or Pythagorean theorem. Whatever it is that we all remember learning, feeling pretty sure it's never going to show up again. But that misses something important. It misses the fact that the act of learning how to do the math establishes a new kind of brain wiring in your mind. A kind of problem-solving brain wiring. So it's not about what you learn, it's about what methods, tools, and tactics you had to develop in order to solve the problem that you may never see again for the rest of your life, but you will see other problems where these methods and tools will become immensely valuable to you.
okay, I started out with that clip because it's very much relevant to this presentation. Now, I know the presentation said blood droplets. That was such a short presentation, I decided to change it to a homicide that I consulted on. Somehow, math and homicides, who would have guessed they go so well together? Not planning the death of your teacher, by the way. No, I'm talking about real homicides here. In my younger days, when I went to college, I went to the University of California at San Diego, and I picked up a couple engineering degrees from them, one in applied physics and information science, and the other in applied mechanics and information science. Then I came out here, and I hired on the police department out here, and I spent about 27 years on the police department. I retired from the police department as the chief. Did just about everything in that police department while I worked my way up the promotion ladder. People use, well, let me just finish what happened. You know, then I went back to graduate school, got a master's degree in math education. I taught up here for about 15 years. Lucy and Sarah were my supervisors. Chuck was my unofficial supervisor, I think. You know, he checked a lot of my work and that sort of thing. And I've been retired from all my work now for about 2 years. Now, math is not normally associated with police work and forensics, but it is very, very relevant because in my career, especially in law enforcement, a lot of the people that I worked with, and this was not designed to be a compliment, by the way, would say, Neil, you think way outside the box, way outside the box. And really what I wanted to say back to them was, I think the box you guys are thinking in is way too small. Because in a lot of ways, my brain was, and it was a privilege to be wired somewhat differently, just like Tyson had suggested that happens. As you start learning math, you can apply some of these problem-solving techniques to any problem that you come up with and be expected for people to say, man, it sounds like you dance to a whole different orchestra. I want to say you guys dance to a 4-piece band maybe, and I dance to an entire orchestra. So anyway, what had happened was, I was going to use this case as one example because in my career, numerous examples, this is just one example where something I did actually in high school applied to this problem. Now, some of you older guys might remember this guy. He's not one that you'd forget very easily. His name's Robert Duke. Anybody familiar? You'd have to be living in Green River. He's a Green River resident. 4 counts of soliciting a homicide, 2 counts of committing a homicide. Basically what this example is about was he was accused of throwing his wife and his 5-year-old son off a cliff and murdering them. Of course, what do you think he said happened? They fell. Okay, and of course, in this country, it is the burden of the state to prove him guilty. He doesn't have to, but he came up with an alternative. He said, I took them up to a bluff, and it was, I can tell you where this bluff is. Easy way to find it is drive to Firehole and look across the lake over to the Green River side. That big monolithic, that's where it happened. Okay, I took them up there for a picnic. I was doing something with the car, I heard a scream, turned around, they had both fallen off the cliff. Of course, that didn't sound too plausible since the wife was deathly afraid of heights, wouldn't go anywhere near a cliff. Oh, by the way, this case did get national attention. Dateline did a whole episode on it, so it was quite a famous case and very scrutinized case. This is kind of the profile of the cliff he threw his family off of. You can see how craggy it is, how crumbly it is. The top of it is nothing but loose rock. You could stand on a rock and the rock could slip out from underneath you and you could fall. When the jury went up there, they killed a rattlesnake. This is not the place you would take somebody for a picnic. You know, and the jury actually realized this very quickly. Well, what happened was, this was going to be a death penalty case. And the prosecutor wanted the sheriff to bring in a number of investigators locally and brainstorm the case. The case was ready to go to trial. They wanted us to brainstorm this thing and say, did you miss anything? Do we have some other ideas that you should pursue before we take this to trial? So that's my involvement. I'm not with the Sweetwater County Sheriff's Office. They brought about 15 investigators from the county and they sat us down and they briefed us on this thing. And so I started thinking about this and I recognized an associated, a similar problem that I did in high school and college that might apply to this thing, which is so often used, by the way, in problem solving. Why reinvent the wheel? If I got a problem that kind of looks like the one I'm facing, can I adapt it? Well, that's kind of what I did. Now, what I proposed is, and there's going to be some math involved here and some physics. If you don't follow it, that's okay, because the conclusions are going to be translated back into English, okay? I needed to translate this into another language, that being math, to solve it. But believe me, if I was going to communicate it to a jury, it better be in English, not in math, right? So just follow along as you can. But what I want you to visualize is a person standing on the edge of this cliff and is a rigid rod. Can't bend or anything, okay? Follow that? Now, I'm not going to push this thing. I'm not going to hit it. I'm just going to tip it and let it rotate off. Follow that? Now, as this thing, can you see it? As it rotates off this desk, does it just fall down or does it launch out? What does it do? Just yell it out. Falls straight down? How many fall straight down? How many says it launches? All right, let's watch it. Now I'm just going to get it tipping, okay?
Neil, how about you do it here for the camera?
Oh, all right. Got it, Eric? Okay, so I'm not going to hit it. I'm just going to tip it so it falls, right? Landed right about there. So there's a launch component. What happens is, as this thing tips over, it gets to a certain angle. I'll call that the launch angle. And then it doesn't take off like a rocket, but it doesn't go straight down. It actually goes out little ways. And that's what this math is going to be about. So there's quite a bit of calculations here, and I'm going to run through it. I'm going to try to run through it kind of quickly, okay? Since I only got 15 more minutes, right? Okay, so what I did is, this is the rod right here, okay? And just for numbers to throw in there, I said it would be 6 feet long, and the center of mass of that rod would be at the 3-foot mark, okay? And what I got it doing is falling like this. You see that? It started up like this, goes like this, and as it falls, this angle increases, and I'll call that angle theta, because mathematicians like using Greek letters because it makes us look so much smarter, you know. Wow, he's great. Wow, theta. I mean, you call it X. Everybody calls it theta. Okay, so anyway, the X position of this, and this is just some trigonometry, is defined by this equation. And I'm not going to go into it, but you guys that follow the math, this is very straightforward. It's just the sine of that angle times its length. And this is the Y position. Okay, so now we'll go into either senior high school stuff, calculus, or first year calculus at college, and I'm going to take the first derivative of both of those. And what that's going to end up doing is giving me the horizontal speed and the vertical speed of this point that is going down. And this last equation, which is the ugliest of all, is the second derivative. And what that gives me is the horizontal acceleration. Now, I'm not going to get too much into this, but this is the key to this equation, or this analysis right here, is this guy right here. This ugly, ugly term. Cosine of theta times the second derivative of theta minus, God, it's even hard to say, sine of theta times the first derivative of theta squared. Now, don't worry about what all this junk is right here. If this term here equals this term, and they're subtracted from each other, it's 0, right? Which makes the horizontal acceleration 0. When the horizontal acceleration is 0, it launches. There's nothing holding it on the table, basically. It launches. That's what I got to find out, is that launch angle. So I'm going to do a whole bunch of analysis here to try to find out when those two things are 0. That's the first part of these calculations, because I need to know what that launch angle is. Questions? Hope not. Okay. All right. Oh, yeah. As part of this, this calculation, I want to get rid of those differentials, because that makes it really an ugly equation. And I'm going to use Newton's second law of motion. But I thought this was kind of a cool video because this is testing Newton's first law of motion. This is worth watching all day long. What? I mean, physics is cool. Look at this. Wow. Looked like a guy was traveling, but he was standing still. The bus was traveling. Okay. That's totally meaningless. This is probably why my supervisors didn't get a lot of sleep at night when I was teaching up here, right, Sarah? You know, it's like, oh, what did he do now, you know? Okay. So I'm going to go through this kind of quickly because I don't think this is going to hold a lot of people's interest. But just so that you believe me, what happens is I use Newton's second law of circular motion. I'm dealing with circular motion here. And what it says is the moment of inertia, which is this guy right here, times the angular acceleration, which is this guy right here. Look at this ugly term. That's the one I want to get rid of, equals the torque. And when I solve the equation for this, this is what I get. And we'll just call that equation 2. I know this is driving the math people crazy because they want to like look at this for a while, okay? Oh, anybody know what torque is? Oh, come on. All right, this is torque. I didn't know they made race cars that little. What? Now, does anybody not have a good idea what torque is now? Again, totally meaningless and not even part of the lecture, but I've been assured there is medication that can help this kind of thing that I got going. But okay, the second thing I'm going to use is the law of conservation of energy. And what that says is the rotational kinetic energy is equal to the gravitational potential energy lost at the center of mass. And what it means is how far it dropped. It lost that much energy. And that's defined by this equation. This is the rotational kinetic energy. And look at this guy. There is the first derivative of theta squared. Remember the other one that I wanted to get rid of? It was like two troublemakers in a class. Chuck. Anyway, I diverge. Anyway, here's my equation now, and I can solve it for this. And notice that now I end up with a far cleaner equation that I can solve for that launch angle. Remember, I want these things to be equal. So now I get rid of this guy right here. This thing is not working very good. I get rid of this thing right here and replace it with this equation. Get rid of this guy and replace it with this equation. And now this is high school trigonometry again. This is easily solved. And it turns out my launch angle is 48.2 degrees. Now, I know at this point, he said, we went through all, I shaved my legs for that, 48.2 degrees. But that was the critical calculation here. And it'll make sense, I hope it makes sense in a second. When I plug that angle, or that angle, into my, remember way back when, my horizontal component of velocity and my vertical component of velocity, I get that at the launch, this thing is going out at 4.6 feet per second and down at 5.18 feet per second. So as this thing, right when it launches, it's going like 4 feet per second that way and 5 feet per second downward. So I decided to just plug those figures in. Where is it at a quarter of a second? Where is this rod at a half a second? Where is this rod at 3/4 of a second, and so on? That's what that is. And I come up with a graph, more math. But this is very visual. What happens is this rod falls, you know, remember that first diagram, and when that center of mass is at 2.2 feet x and 2 feet up y, right? It launches, and this is the trajectory. And I don't want to go into, I mean, I was just plotting points and stuff, boring stuff. But look what I did was, part of their investigation is they did a vertical survey. They had surveyors out there, did a vertical survey of the cliff profile. And when I matched that on the graph, here's the cliff profile, here is the trajectory. There's an intersection. And I can point to a physical spot on that cliff where that intersection is. Now that's based on what? A rigid rod. So now let's get a little bit away from the math and let's talk in English again, because that's important in math. Math is a foreign language. I tried to get my advisors to allow that to fulfill my foreign language requirement. They wouldn't do it. I said, let me hear you talk math. But I'm translating back now. Let's just think what would happen if I was standing on the edge of this cliff and I fell. I'm not going to maintain this straight rod. I'm not going to be a straight rod to begin with. I'm probably. Yeah. And if I start to fall, likely I'll turn towards the cliff. You'll start seeing fingernail scratches probably at the very top, all the way down. In fact, you're going to see some kind of biological transfer or disturbance on that cliff from the very top all the way to the bottom. The only time there'll be a gap is if you bounce. And that's horrific to envision, but that's what actually happened. I'll get into that in a second. Any comments on that? Okay, so let's look at the other scenario. What happens if they're thrown off? Well, likely there's going to be a struggle, especially with the wife. She's seeing murder now, and she is likely going to be fighting. The kid's going to be fighting. And there's a good chance they might have just rolled off the top of this cliff, and there could be biological transfer all the way down the cliff. Here's my conjecture. What if there isn't? What if there is no biological transfer till the intersection? What that tells me is they had to be thrown. So a forensic examination of the profile would be necessary. So that was my conjecture. That's what I came up with the brainstorming. And of course, most of the other investigators would say, ignore him. He thinks way outside the box. I did agree that my brain was wired different. So anyway, since this was a death penalty case, I got to hurry up now. But the county attorney calls me up and says they're bringing in a fall expert. And he needs help pay. I was chief at the time. He needs help paying for this guy. He wants the sheriff's office to pay, the county attorney's office to pay, Rock Springs PD to pay, because this guy charges by the minute, and he actually did. His charges, it wasn't by the hour, it was by the minute. And Rock Springs had a death penalty case going at the same time. He said this expert's going to help in analyzing our crime scene, which is a whole nother presentation. So anyway, I agreed, of course, sheriff agreed. And they brought this guy in, and he was a professor from a college back east. He brought crash dummies. He brought, I think, 5 of his graduate students out here. And yeah, he was expensive. And we did the crash dummy test off the top, and what the math predicted is exactly what the crash dummies did. The videos of those crash dummies going down was just, I know they were crash dummies, but this was a homicide scene, and it was just horrific. So anyway, he gathers all the investigators back together after we do the test drops and stuff, and he said, "Who did the math?" Well, he did. You know, I mean, everybody was like, okay, he did. And I'm thinking, oh my God, you know, maybe I should have Chuck check my, you know, my figures. He goes, "That was remarkable." He says, "That's exactly what we do." He says, "That's exactly what my analysis is, you know." And all of a sudden, my box didn't seem so small anymore to everybody, you know, especially if now I get the idea I can charge by the minute. So that's it. Thank you. Thank you.
All right. Anybody have any questions for Neil?
What's your rate?
It's 3 Skittles a minute.
Yeah, I got my Skittles here, so yeah.
All right,
By the
so-
way, he was convicted, but not the death penalty. He got, I think, 6 life sentences or something like that. I think he got the death penalty, but that was overturned in some sort of appeal process.
All right, so we'll do a raffle real quick, 1 through 24. And just a reminder, when you come to these math talks, they make your math teacher happy, your first year success teacher happy, English teachers happy, and communications. So 4 for 1 deal, right? So please let your teachers know that you attended. 10. Number 10. Samantha.